Hi everyone, in this video I'm going to mess about with some resistors. I'm going to wire them in series and parallel and whatever I think of at the time, and I'm going to see what happens on multimeter. I think we've all got a rough idea of what's going to happen, but anyway, it'll be an interesting test. So to start with, what are these things? Well, these are ceramic or cement resistors, and from what I remember, there's a thin wire of coil in there, I could be wrong, and it's set to the resistance which it's meant to be meant to deliver, and then it's encased in this cement-like material, and hence I believe that's why it's called a cement resistor. So anyway, what are these things? What does it say? So it says 10 watts. 10 watts is the amount of power it can safely dissipate without destroying itself. So you get the idea. 3.3 ohms is its resistance, and J is something to do with the tolerance. And I don't actually know what J represents. You're doing YouTube tutorials and you don't know what J represents? Shame on you, blah blah blah, whatever. But yeah, I think it might be 5%, but I'm not too sure. That's just off the top of my head. Anyway, so they're the resistors, and I'm just going to do some tests. Right, so let's get started. So before we do get started, actually, there's just something that I need to point out. Let's say I had an excellent conductor here, so like gold for example, and I had a tiny little piece of 1mm, and I went to measure its resistance, and I put the probes on it like that. For something that has such excellent resistance, what reading will I get here? Well, you probably should get something like 0 ohms or 0.01 ohms or whatever, but you won't. And if I measure this here, which the space between the two probes is pretty much no resistance, look at what I get on the meter. I get 0.3. And you could be thinking, well, how can it be 0.3 when I'm not actually measuring anything at all? And the reason is, of course, because these leads have a resistance, and let me just show that again. The resistance of the leads is 0.3 ohms. And anyway, the reason why this matters is because when I'm dealing with precision resistors and stuff, you know, 0.3 ohms is a big deal. Anyway, so let's get started. To start with, I'm going to measure the resistance of these two resistors. So let's start with this one, and they are 3.3 ohms. I don't know if it can work it out because the light's quite bright, but 3.3 ohms. So what should I get here? I should get 3.6 ohms, right? Because the leads have a resistance of 0.3 ohms. So 3.6 ohms is what I expect. And I get 3.6 ohms. Perfect. So that is 3.3 ohms. Right, the next one, let's just make sure. Because of this J business, there might be a tolerance. So here we get 3.5 ohms. So that's very interesting. So that makes this a 3.2 ohm resistor. Oh, that's very interesting. So, if we've got a 3.3 and a 3.2 and we put them together, what will we get? Well, of course, we'll get 6.5, right? 6.5 ohms. And we've got this as well. So we should get 6.8 ohms. So 6.8 ohms, and let's try this out. 6.8 ohms. I need to have a good connection in the middle here as well. 6.8 ohms. So that's a 6.5 ohm resistor if you put them in series like that. So that's very interesting. Now what do we expect to happen if we put them in parallel like this? Well, if you put them in series, of course you add the resistance together. But if you do it this way, you actually split the resistances between the resistors. So let's just see what we've got again. So we've got a 3.3 and a 3.2. So because we've got two resistors, if we add them both together, we get 6.5, is that right? Let me just check. So yeah, 6.5. So if we divide that by 2, we get 3.25. I think that's about right, isn't it? 3.25. Yeah, 3.25 ohms average. And now, because they're both together, we have to, and there's two, we halve the amount of resistance if they're in parallel. So what did I say? 3.3 3.25, something like that, 3.25 ohms average. So that's half that, so that's 1.5, 1.6, 1.65, something like that, 1.6 ohms. And then this has the 0.3, so if I measure this I expect 1.9 ohms. 1.9 ohms if it's in parallel. Oh, this is really awkward. 1.9 ohms. Ah, 1.9 ohms. Okay. So both together, that's actually 1.6 ohms. So yeah, if you get two resistors that are identical and you put them in parallel, the amount of resistance when they're in parallel is half. So yeah, 1.6. That's very interesting. Okay, so let's mess about a bit more. I've got three resistors now and I've put them all on this breadboard, and they're all in parallel. So let's just get some wires and just check the resistance of these wires. Okay, so that's 0.8 ohms. Oh, 0.7 ohms. So that's actually 0. Is it deciding? 0.7, yeah. So that's 6. Okay, so this wire is 0.3 ohms, which, well, whatever. 0.3 ohms. Let's put that in there. And test this one. So this will be 0.3 as well. So it should be 0.6 in total. What? 2 ohms? That's not good for such a little piece of wire. I think I'll get rid of that one. Try another one. Let's try this one. 9 ohms. These wires aren't very good. Let's try this one. With this one being longer, it should be even more resistive. Zero. What? That's actually less resistive. Oh, okay. Well, 0.5. So that's 0.2 ohms. That's really interesting. Anyway, I'll push this in. Okay. So what am I going to do with these now? Well, I'm going to just assume they're all 3.3. So what should happen now? So basically, because they're all the same, there's 3 of them, we'll divide them by 3 because there are 3 paths now. That should be 1.1 ohm. So if I check the resistance of these now, or this thing here, because basically now this is a new resistor, it should be 1.1 plus 0.3, so it should be 1.4. Yes, that's very interesting. So I've been sat here for about 5 minutes wondering how the hell I'm going to explain this phenomenon that when you parallel in resistances, it actually lessens the resistance. I was thinking, how will I explain that? But actually, it's quite simple. It's hard to explain though. But I'll give it a go. So to start with, let's forget about these resistors. Let's forget that they're resistors. Let's just assume they're conductors. So if we assume they're conductors, because actually they are, I'll just put those to the side and let's simplify it and use these wires instead. Now these wires are conductors, but they're also, if I want them to be, they can be resistors, and that's because these wires have resistance in them. So with these, we call them resistors because we know the exact resistance, but these can also be resistors too if I want them to be. Anyway, so they're just conductors. So now I'm going to bring in this. So let's say we have one wire and we plug it in and we've got a 10 volt source here and we've got a 0 volt here. There's a 10 volt drop across this. Well, what happens if we add in another one in parallel? Well, the resistance drops, and the reason being is because there's more surface area. So there's more surface area, less collisions at an atomic level, because electrons fly through the conductor, and if there's a lot of resistance they hit into ions or eons or whatever they're called, and it causes heat, and particles fly around everywhere. So what happens if we add another one? The wire gets thicker. There's now less resistance because it's purer on a electronic level, if you like. So what about now? Well, this wire is very thick. It's much thicker than these ones, and therefore there is less resistance. Now, hopefully this is becoming clearer now. So the thicker the cable is, the less resistance there is, and that's simply because there's more conductive area, if you like. So now coming back to these, hopefully that kind of makes sense now. So even though these are resistive, they are conductors, but they've got a resistance. If you add them together, then you've got more conductive area than not, and therefore, if you parallel them together, the same amount of electrons fly through, but there's a much greater surface area, and therefore there's less loss, and that's why it works that way. So I hope that explained it reasonably well. It's quite a difficult thing to explain, but anyway, I hope that helped.